I play this because here we have Take It Easy, which starts off by saying, I've been running down the road trying to loosen my load. There's been 7 women on my mind. Then the second song on the album is called Witchy Woman. You can draw your own conclusions. The third song is Lying Eyes. Let's hear what he says. Okay. Using many worlds to solve the unsolvable was the original title of this talk. It's not the title that was in the brief, I'm sorry, but it's essentially the same talk. So maybe I lied, maybe you came here on false pretenses. I'm James, nice to meet you all. I used to work for a company called ThoughtWorks, which is, I think, the best company in the world. I'm sad that I don't work there anymore. Now I work for a company that really wants to be like ThoughtWorks, called Coherence. I've been in Kyiv for like a couple of days, and I was disturbed when I got to the hotel that there was no floor 0. Now this always upsets me when I get to somewhere, some city. It's like, I mean, use your numbers correctly, you know? Start from 0, please. But not as bad as this hotel I went to in Porto, which had a -1 and a 1, but no 0. I cannot now return to Porto because of that. It's impossible for me to go there. I walked through this big square in Kyiv, it's lovely. And yesterday I got completely lost. Ended up in an industrial estate, which, you know, maybe it was once a nice place, but it's not particularly nice now. I also got lost today, which interested me, but this is yesterday. There was a lot of talks yesterday, and they all got ranked, which I think is lovely, although I don't particularly think we should have a competition. What was interesting, though, is that one talk had 23 ratings for 4.57 score, and the one at the top had an average of 5 off 1 rating. Perhaps we shouldn't count the score from the speaker. Just saying. This was yesterday as well. There was no beer in the party. Why? Because there was only Jack Daniels. So this is Chris Tanninger. We bought him a beer called, yeah, I mean, you can't see it, but it's actually called Tanninger. And he did a fantastic talk this morning. This morning also, I got up quite early to go and watch the rugby. Nobody else cares about the rugby. I do, I'm English. What happened? Well, there's me watching the rugby. And we lost. And this belongs to yesterday's talk. But outcome over process always. I won't spend too much time on this. Here's a South African guy that's going mental because they won. And obviously, me being me, I videoed the end.
Three, 2, 1, go. That's it. Yeah!
And actually, that's the bit I want to focus on, because that is Prince Harry, and that is Cyril, I can't remember his name, but he's the black president of South Africa. And I thought it was fantastic that in 2019, that's what we see. So, there's a guy that claimed to be English, but really wasn't. And as I sent a message to a friend of mine, they executed better on the day. That's what sport's all about. Nobody cares about the semi-final. Maybe England played the best ever game in the semi-final, but nobody cares. Because you know what? South Africa executed on the day and won the match. What you should care about is outcomes, not how you got there. Sorry, that was yesterday's talk. Oh yeah. Google Translate always works. And she did give me a selfie in the bar. As did the Irish people standing with me, which was great. But here's the biggest message. Kolisi, the South African captain, is a black guy. And for me, I'd say take that forward. And the reason why I was playing the Eagles when everybody walked in is because I love that music. I'm not saying the Eagles are crap or anything, but those three songs, Take It Easy, Witchy Woman, and Lying Eyes, listen to the lyrics and ask yourself, could anybody write a song like that in 2019? They wrote those songs in the 1970s, the 1980s. I don't think they could write them in the 1990s even. So, happy to have that conversation in the bar. Let's move on. Oh yeah, one more thing. After my talk finishes, go and watch this talk by Fiona Cove. It's a great talk. Everybody go into that room. Okay, I'm going to talk about quantum computing and quantum cryptography. Here we go. Oh yeah, we're going to start with a pub quiz. Does anybody remember the Beast from the East? That's what it was called in the UK. It was during 2018. We got snowed in a pub in March, and it was amazing, and we ended up doing a pub quiz. So that's why that photo came from there. So here's a pub quiz. I can't actually remember what it is, but let's have a look. Go away. Right, does anybody know who these three people are? Not you, Fiona. No? No guesses? Anybody any the wiser as to who they are? And by the way, I apologize for the lack of diversity at this point in the talk. Well, they're three people. Does anybody have a guess at who these two are? I'm talking about cryptography. Do you want to have a guess? Did anybody say Diffie and Hellman? No? Oh, God. It's a tough audience. All right. Come on, have a guess who these three people are. Huh? Okay, I'll give you a clue. They form an algorithm. They form RSA. They could be. Let's have a look. Rivest, Shamir, and Edelman. We'll come back to those people. Right. This is cryptography. The whole point about cryptography, and we always talk about this, is that Alice needs to send a message to Bob, and she needs to send that message such that Eve doesn't interfere with it. Now, it's crucial to understand that Eve, from Eve's perspective, she needs to read the message or hear the message without them knowing that she's done so, right? So it's only valuable to Eve to read the message if they don't know she's done it. And that's essentially all there is to cryptography. How do we make that happen? So from Alice and Bob's perspective, they want to make it unbreakable. From Eve's perspective, she wants to break it, but such that they don't know. So, how do we do public key cryptography now? Well, it's essentially down to maths, which I don't have time to explain, and I hope that everybody in the room understands it anyway. It all comes down to finding something that's easy to do one way and hard to do the other way. And essentially, what RSA relies on is the fact that it's easy to multiply together two large numbers, but it's hard to factorize a very big number. Okay, we'll come back to that. Has anybody in this room used quantum computers? Am I really the only one in this room that's used a quantum computer? Oh, God. Okay. So what, in that case, let's see. In order to understand quantum computers, you have to understand what classical computers do. Classical computers manipulate bits. A bit is a 0 or a 1. This thing here, this is a very simple representation of an OR gate. If either of these things is closed, the light goes on. That's an OR gate. Logically, that's what computers do. On the right-hand side there, you've got a combination of OR gates, XOR gates, AND gates, NAND gates, which go to make up what that picture is actually 16-bit floating point arithmetic. And when you sum together loads and loads of different gates, you get different operations, you get different stuff. That is all classical computers do. But they do it on such a massive scale that it turns out that it's quite useful. Now, What quantum computers do is they have something called a qubit. A qubit is a quantum thing. It could be a photon, it could be an electron, it could be part of a nucleus, it could be a lot of things. But essentially, it's a thing that when you measure it will either give you a 0 or a 1, but every other time it can have both values. You can think of a qubit, a quantum bit, as a point on that sphere there. That's supposed to be a sphere. I'm sorry, it's not my picture, but it's the best picture I could find. The quantum state is represented by that thing there. I think that's a Greek letter called psi. I think it's psi. The closer it is to the top means that you're more likely when you measure it to get a 0. The closer it is to the 1 at the bottom, the more likely it is that you'll get a 1. However, until you measure it, it has both values. So the crucial thing to understand is that when we're using quantum computers, if you have an array of these things together, these qubits, if you make them do a calculation, the quantum computer will calculate using both values. And that's really one of the reasons why they're powerful. I'm going to cough, excuse me. Thank you. And in a quantum computer, you have gates just like you have the AND gate, the OR gate in a classical computer. There's a load of different gates. If you're interested, go to IBM Q and you can program quantum computers yourself. Okay. Now I'm going to play a quick video, if I may. Not that one, though. Not that one either. This one. I hope the sound works. The three of us have been trying to reproduce the double slit experiment. So this is Ben, this is James, and I'm James as well. We've used equipment that you can find anywhere. Well, 3D printer maybe. Yeah. Wow. Down here, we made a frame and a holder for our double slit. We made the double slit by using a sharp knife in between some tin foil. Here we have a laser pointer. It's the same laser pointer that I'm going to be using during the presentation. So who knows, I might even reproduce it if I've got this equipment, but it'll probably end up in the bin later. Down this end, we've got 3D models of Ben. We've got Big Ben and medium-sized Ben. Little Ben we left on the table over there somewhere. And they're holding our screen to receive the results. So let's see if we can make a diffraction, an interference pattern at the other end of this desk. It's very scientifically done this, and there it is. Can we see the interference pattern? And that is quantum physics in action, as demonstrated for you in the ThoughtWorks office. Thank you very much.
Well, that was perfect for a second.
Yeah, we get a really good shot of it. Okay, what's going on? So that experiment was devised by a person called Young, a physicist in the, I think that experiment was done in 1809. And at the time, before he did that, the prevailing theory was that light traveled as particles, which Sir Isaac Newton had called corpuscles. And Young didn't believe that. Several physicists didn't believe it. So he devised the double slit experiment to show that light traveled in waves. And there's a schematic of what's going on, because the waves, when they go through the two slits, they interfere. You get positive interference, you get negative interference. And that's why we see that graded pattern that we see at the end there. So here, through the middle, there's positive interference, then there's a dark spot, then a bright spot, then a dark spot, bright spot, and so on. So in 1809, what that meant was, hey, yeah, I've proved that light travels in waves. So everybody in the world goes, yeah, brilliant. However, it turned out that when we started understanding quantum mechanics, that light doesn't travel in waves. Light travels in these little particle things called photons. Nobody really has ever seen one, obviously. But clearly there's an interference pattern going on. So in the 1920s, the Copenhagen School of Quantum Mechanics, they said, well, clearly interference is going on, so therefore these particles that we know are carrying the light, let's invent something called wave-particle duality. So they behave like waves, but they also behave like particles. So everybody was happy for a while. Until about just after the war, it was possible to make an experiment where you could have a photon emitter and a photon detector with double slit in between, and you could guarantee that only one photon was traveling through the air at the same time. So you fire a photon, you wait until that photon hits the screen, then you fire another photon through that same apparatus. And what happens is that you still get this interference pattern. So every photon is going through an interference behavior, but there are no photons flying through the air at the same time. How does that happen? Well, the interesting conclusion is that every photon takes every path, every possible path. And much as it's hard to get your head around, that's the only explanation of what's going on, and all of the photon paths are interfering with all the other photon paths. We can only see one photon, but every other photon travels through different universes and hits the screen. That's why we get this interference pattern. So, we'll come back to that. I apologize, sorry. This is my daughter's cat. She is showing the only mood that cats show, which is obviously indifference. We decided to run an experiment with the cat to see that if it was possible for the cat to hold different moods at the same time. It turns out you can have different moods at the same time. That joke only ever works in English, so let's move on. Interference and superposition underlies something called the Quantum Fourier Transform. Has anybody heard of the Fourier Transform? Fantastic. The Fourier Transform converts the time domain to the frequency domain, effectively, or the other way around. And in quantum computing, the Fourier Transform relies on the fact that all of the photons interfere with each other. All of the qubits in your computer interfere with each other. And that gives us the power. We will come back to it. Hold that thought. God, I wish I wasn't coughing. Right. How long have we got? Ages. Has anybody heard of Shor's algorithm? Excellent. Does anybody understand it? Okay. Shor's algorithm is about factorizing large numbers. So, how does it work? Well, I'll show you. You pick a random number. We're going to factorize n. Now, let's say n is a number, a big number, massive. Pick any number less than n, find the greatest common divisor. If it's not 1, you've found the factor, but that doesn't happen often. Step 4 is important. We'll come back to that. Then there's some linear algebra, which you can probably understand. Right, so here's an example that you might get your head around. Let's say we're trying to factorize 15. I'm going to choose a random number less than 15. So I'm going to choose 2. Now, 2 is not a factor of 15, so move on to the next step. I'm going to find the period of 2 with respect to 15. So 2 squared is 4, 2 cubed is 8, 2 to the power 4 is 16, which is 1 mod 15. So if we continually raise it to successive powers, it goes 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. So the period of 2 with respect to 15 is 4. Does everybody understand that? It was quite simple, I think, I hope. So, what does that tell us? It tells us that 2 to the power 4 is equivalent to 0 mod 15. Is that right? No, it's equivalent to 1 mod 15. So if we take the 1 over the other side, what that tells us is 2 to the power 4 minus 1 equals 0 mod 15. You can factorize 2 to the 4 minus 1 into 2 to the 2 plus 1 multiplied by 2 to the 2 minus 1. As we see now. So 2 squared minus 1 is 3. 2 squared plus 1 is 4. That gives us the factors of 15. I think we all understand that 15 is 3 times 5. Now, I went through this exercise myself one day when I was traveling to London on the train, and I forgot to open this spreadsheet, for which I apologize. Unless it's one of these. Let's have a look. Oh no, that's flats for rent, and that's my money. Running diary, we don't need to see that. Oh no, that's a competition I have with my family about Strictly Come Dancing. We don't need to know that, do we? It's an English thing. So I wanted to understand how Shor's algorithm works. So what I did was I decided I would factorize that number, 1,517. So I started by choosing a number less than 1,517. And on this first sheet, we see I chose 4. What we're doing is we're raising it 4 squared, 4 cubed, 4 to the 4, and so on, down there. Eventually, because we're doing it modulo 1,517, we know that it's going to go back to 1 eventually. So let's see how long it takes. There, 90. So 4 to the power 90 is 1 modulo 1,517. So what that tells us is that 4 to the power 45 plus 1 and 4 to the power 45 minus 1 are multiples of the factors of 1,517. However, that's not useful because for my demonstration, I wanted it to be something that I could actually have numbers that I could work on. And as you can see, it overflowed at 25, so 4 to the 25 overflowed. So I thought, okay, that's no good for my purposes. So I tried 16, which again overflowed, although its period was quite small. Oh yeah, 16 doesn't work because it's an odd number. So 16 has a period of 45, so we can't do 16 to the power 22 and a half, so that's no good either. And then I tried this number, and that number, and so on. And then eventually I got to 10, and I was excited because 10 had a period of 15, and I thought, yes, it doesn't overflow. But then I said, oh, it's an odd number. That doesn't work for me. So that didn't work. But then I found that 14 has a period of 24, as you can see. But crucially, 14 to the power 12 does not overflow. It's an integer that hasn't overflowed in Google Sheets. So that gave me the ability to factorize 1,517. So how do those maths look like? I will find this presentation here somewhere. I think it's in that. There it is. So we chose 10. It was an odd number, so I go back to step 1. Then we chose 14. The period is 24. So 14 to the power 12 minus 1 is this huge number. The greatest common divisor of that and 1,517 is 37. 14 to the power 12 plus 1 is that other big number. The greatest common divisor of that big number and 1,517 is 41. So I factorize 1,517. It is That wasn't my question. Go back. It's 41 times 37. So, where's the magic in that? Well, you can see from that spreadsheet that that whole business of calculating the period of a number is very complex. It's actually exponentially complex to find the period of a number using a classical computer. But Shor's algorithm does this. It says use the quantum period finding routine to find the period of a to the x mod n. Now, what it does is, imagine if we could do my spreadsheet that we just showed. Imagine we can do that for a massive, massive number, but we don't care about all of these other numbers in between. All of these numbers in column C, we don't care what they are. All we care about is this one number here. So we don't care about these huge integers that overflow. Using a classical computer, you have to do all that calculation to work out the period. All we care about is that. Now, in a quantum computer, by using the Quantum Fourier Transform, you can simultaneously carry out all of those calculations as they go in parallel universes. Believe me, it's true. And by studying the interference pattern, as we saw with us seeing the interference pattern in real life in that video, by looking at that interference pattern, we can work out the period. Okay? So, if you hold that thought, what Shor's algorithm says is, and what we can do in a quantum computer is, without doing all of those intermediate calculations, we can find the periodicity of not just this function, but any function, by applying the Fourier transform and looking at the interference patterns. That is the power of quantum computers. Because they can do that, what happens is that all of those calculations take place in parallel universes, believe me. But we don't care about the results of the other calculations. All we care about is that periodicity. That's the power of quantum computers. So, oops, I didn't mean to do that. That's where the magic is. So, if you want to see an implementation of Fourier, of Fourier and of Shor's algorithm, on my GitHub, it's there. I don't like my own implementation, so I would recommend that you don't particularly look at that. I would recommend you look at this guy's implementation, who was one of my ThoughtWorks colleagues. And actually, this was an illustration of what's great about people that are new to the world of software development and everything, because I said to this guy, he started working in my team, and I gave him a book on quantum computing, and I said, look, I want to understand how to implement Shor's algorithm. Do you think that you can go away and read this book and then come back and see what you can do, and we can talk about it? And a couple of hours later, when I was on a train from Manchester back to London, he sent me this message saying that my algorithm successfully factorized 35 after an hour and a half. And I was like, wow, good lad. Should we talk about this? So if you want a good implementation of Shor's algorithm, look there. Look on Andrew Breyer's GitHub. So if we can factorize large numbers, if a quantum computer exists that can factorize any arbitrary large number, should we be scared? Is RSA finished? Well, it's an interesting question. I think it is, but let's move on. To implement Shor's algorithm in a real quantum computer requires, as far as we know, Shor's algorithm is Shor's algorithm is polynomial complexity, but we also know that to implement Shor's algorithm, you require 3 times as many qubits as the size of the key. So if you've got a 2048-bit key, which is the current RSA standard, you would need in the region of a 6,000 qubit computer to decrypt it. Currently, that's out of scope. Also, if we were to move to the next level, 3072-bit keys, which are in use in certain places, if you were to construct a computer, a classical computer, out of which used every single electron in the universe as a computational bit, it would take that computer longer than the lifetime of the universe to factorize a 3072-bit key. So, it's safe to say that RSA is safe from attack from a classical computer. But it's not safe from attack from, there you go. Yeah. It's not safe from attack from a theoretical quantum computer. Google last week announced that they have achieved quantum supremacy, which means that they, for the first time, have shown that their computer can solve an algorithm. There is a problem, a real-world problem that exists, which is solvable more efficiently with a quantum computer than a classical computer. The reason why this is important is that I think that it starts to, there will be that was the tipping point we were waiting for. That means that now banks will pour billions of pounds into investment in quantum computers. Government will start pouring more and more money into it. Governments have already been pouring more and more money into it. So, what happens if RSA dies? Well, I'm going to explain BB84 in a moment. BB84 stands for Bennett and Brassard. We'll come back to that. There are quantum-safe algorithms. We're not using them right now. Lattice-based encryption is something that I don't understand. Neither do I understand singular, supersingular, elliptic curve, isogenic cryptography. Open quantum safe has been there since 2016. It is an open discussion for the whole world about what we do when quantum computers break current encryption. What I do know is that there's something called ring learning with errors, which I think might be on the next slide. Yeah. Ring learning with errors, RLWE, is an algorithm which is thought to be quantum safe. I can't stand up here on stage and guarantee it's quantum safe, but essentially it uses a polynomial as the key for your encryption instead of just one number. That's thought to be safe from attack from quantum computers. However, there is one thing that is 100% safe, and I will now show you another video.
We're going?
Yeah, we're going.
Right, I'm James. Today, we're going to do another quantum experiment. This time, we're going to talk about polarisation of light photons. Here, my daughter Felicity, and here, we've got my daughter Clementine. Okay, and outside, what have we got? We've got the cat. That is...
It's definitely very helpful.
That is Clementine's cat, and as you can see, she wants to get inside. Girls, does one of you want to empty this box out just to show Amazon's packaging? And what was it they sent us through the post? Well, it was these 3 tiny pieces of polarizing light filter. Okay, now, let's run our experiment. Girls, if you take one, Clementine, take another. So you take those. Take them over to the window. Okay, so now the girls have got the 3 light filters. Clementine's got 2, and Felicity's got 1. Okay, so now Clementine, if you hold 1 light filter up to the light, that's it, that's good. Now, hold it so that it's facing right towards me. So it's flat towards me, that's good. Okay, now, bring the other light filter up, Clementine. And that's it. Now, they're at right angles to each other, and you can see that where they overlap, no light is getting through. If you just rotate it round again, so it's the other way around, Clem, you can see that when they're in the same orientation, it still lets half the light through. So now, if you put them together the other way around, that's it, hold them tightly against one another, that's it. No light is getting through. One of the filters is stopping all the light, the other filter's stopping the other, all the rest of the light. Now, Felicity, get the other filter and hold it in front, so it's touching. You can see still nothing's coming through the 2 filters that are touching. And on the back, please. Okay, still nothing comes through the two filters. Now, slip it in between the two filters. That's it, brilliant. Now twist it towards you, and make sure they're tight at the top. Hold it there. Fantastic. Now you can see what's happening. Where there's one filter, some of the light stopped. Where there's three filters, some of the light stopped. Where there's only two filters, all of the light is stopped.
Why? Why does it work like that? Well, that's a bit of a paradox, I think we agree. Because if you would think that by introducing another filter, surely, oh no, that's not it, excuse me. So, the situation is one of the filters stops half the light. Two filters together at right angles stop all of the light. But if I introduce a third filter in between, it stops most of the light, but not all of the light. And we could see when we were rotating it that it varied. The amount of light coming through varied depending on the orientation. This is what's going on. I have to say thank you very much to our designer at Coherence for redesigning my original slide on this one. So, light travels, each photon has an orientation, which we can see. This is a reasonable representation of it. The photon points in a direction somewhere in the 360-degree plane. So, if the photon is at right angles to the filter, it will not get through. 100% of the time, it will not get through. If the photon is aligned with the filter, like this one here, 100% of the time, it will get through. However, every other photon has a probability of getting through based on its angle. But what happens is, all of the photons that get through, so half of them get through, but the filter changes the orientation. After they go through the filter, they are all, with 100% probability, aligned exactly how the filter was. So, in the first picture, when we then introduce a second filter that is at right angles, perpendicular to the first filter, nothing gets through. Because 100% of those photons are perpendicular to this filter, so they can't get through. So that's why when we had two filters together, they can't go through. So, what happened when we introduced the third filter? Well, the first filter still changes the orientation of the photons that go through. Then we put a filter at a 45-degree angle. So, what's going to happen here? Well, exactly half of these photons will get through this filter, but they will change their orientation like that. So exactly half of those first level of photons get through, they will change their orientation, and now, when they meet this third filter, of course, half of them will get through that third filter. That's why we actually see 12.5% of the light getting through. So that's why introducing the third filter in between changes the result. Why is that significant? Well, we'll come back to that in a moment. If you remember, right at the start, I said that the key to, I shouldn't say the key, the crucial part of cryptography is that Eve wants to read the message without Alice and Bob knowing that she's read the message. So, if there's a way for me to know that she's read the key, that's good. So, what happens is, we can exploit the fact that by reading the message, if we go back to here, every one of these photon filters can be considered to be a photon detector. But the crucial point is that by reading the state of the photon, I may change it. So in that first filter, if I read it correctly as horizontal, and it was horizontal, great. But if it was anything else, I have disturbed its state. So, moving on. How does BB84 work? And this is the future of cryptography. Essentially, Alice and Bob agree to exchange their key based on, it could be photons, it could be other quantum things, but let's stick to photons. I'm going to send you my key based on something like that or something like that. Okay? So as you can see, if I'm gonna send the photon in this orientation, that means 0, that means 1. Or I could use that to mean 0 and that mean 1. But I'm not going to tell you in advance how I'm going to do that. So what happens is I randomly generate the basis and the key. Is everybody with me so far? Cool. We can all go to the pub soon, don't worry. So then, Bob does not know what Alice was using as the basis for the key. So Bob has to randomly choose something, right? So here, Alice chose to send it diagonally, and Bob measured it diagonally. So 100% of the time, Bob will find the right measurement. Here, Alice chose to send it perpendicularly. I don't know the opposite of what diagonal is, sorry. And Bob measured it that way. So this measurement here is random. Okay? Everybody with me so far? So sometimes Bob chooses the right way to measure it, sometimes he chooses the wrong way to measure it. So Alice and Bob communicate publicly, and Alice says, this was the basis that I used. So Bob looks at his results, because he knows how he measured every bit of the key. They basically throw away all the bits where they didn't agree. And that becomes the shared key. So the crucial piece is that the message has to be shorter than the key. So the key has to be quite long. Why is that provably secure? Well, if Eve was in between that communication, Alice and Bob know she was in between the communication. Because just like Bob, she didn't know what the basis was that Alice used. So, if in between Alice and Bob, Eve was there and read what the alignment of the photon was, she doesn't know how it was sent. She cannot possibly know whether she was using the correct measurement or the wrong measurement. And she will disturb the measurement that Bob sees. So, you cannot guarantee that the key isn't read, but you can guarantee that you know it was read. So essentially what BB84 does, it says, you then continue to send the key until you know it wasn't interfered with. So it is 100% a secure algorithm. And there are networks that are doing this already in the world. At the moment, their effective range is about 140 kilometers, but I know the UK government is investing in it. I was at a meeting last week about this. This is happening. This is the future of encryption, or at least this is 100% secure. There are other ways to also be secure. So that's the point. If Alice and Bob know that Eve was eavesdropping, so what you've got is a one-time keypad that is guaranteed to be secure. Lovely. As I say, it's in use. There are quantum key distribution networks in use. At the moment, you have to trust the organization that owns the satellite. And there is a Chinese satellite in orbit that is doing QKD. I personally don't trust it. It's up to you if you do trust it. As I say, the UK government is working on it. The original demonstration, by the way, is called BB84 because it was developed by two people called Bennett and Brassard, and they did it in 1984. And I think they were working for Bell in the USA. And they transmitted a key over 1.2 meters. So that was really useful. So, I'm going to finish with a brief history lesson. Mercifully, this is a short talk, so we can move on. Does anybody remember that desperately undiverse slide at the start? All these people. So, why should I care about Shor's algorithm right now? Well, in 1976, Diffie and Hellman, I think they're on there somewhere. Diffie is, or Hellman's the guy with the long hair. They published a paper called, oh, there it is. I haven't got my glasses on. Oh, I have. They're there. Multi-user cryptographic techniques in 1976. That was the first time that somebody proposed a way to do key exchange publicly, which was seminal. There was a beautiful piece of maths. I loved it. Well, I wasn't around in 1976. Well, I was, but I was 2. But, you know, when I studied it at university, I loved it. The maths was beautiful. In 1977, Rivest, Shor, and Adleman published their RSA paper. Great. So we all know about that. And then they patented RSA. And then shortly after that, the US government made a law that outlawed exporting RSA beyond 40-bit keys, which was amazing for the tech industry all over the world because it meant that American companies weren't in the encryption business. Great, that was 1977. But in 1997, so 20 years later, those 3 people that nobody's heard of, Ellis, Cox, and Williamson, they had developed an RSA algorithm at some years before the papers were published. Obviously, the British government didn't tell us at the time, and we only found that out in 1997. And I think it's reasonable to assume that several other governments in the world similarly had such encryption. In 2019, we know that there is enormous government spending on quantum computers. And we know, because Shor's algorithm is proven to be useful, that that will start to break RSA encryption. So I think it's reasonable to assume that all of the NSA, the British government, everybody else's government will be storing, in fact, I know this for a fact, they are storing all of our messages now. Anything you send today, which is RSA encrypted, is being stored. If you care about the privacy of that message today, that's fine, because nobody can read it today. But if you care about the privacy of that message 5 years from now or 10 years from now, whenever the quantum computers come that can decrypt it, you should be very scared, and you should not be using RSA, because all of those messages will be just as breakable 15 years from now, 10 years from now, 5 years from now, as they are now. So please, we need to move on from RSA. Thank you very much. Apparently I can take questions. There's a question there.
Just a remark. Somebody I know works in a company and they actually do store all the traffic. So it's not a theory,
They do
it's a
store
fact.
what, sorry?
They store all the traffic. It's not a theory, it's a fact.
No, I know it's a fact. I ran a quantum hack day in London about a year ago. There were people from Oxford University and Cambridge University and lots of people there, and one of the Oxford University academics took me aside and said, "Do you know everybody in this room?" And I said, "Well, no, of course I don't, you know." And he said, "Well, can I have their names?" And I said, "Well, sure, I'm happy to share them with you. That's where we're all open." And he said, "Right, I think that person and that person work for MI6." And I said, "Come on, really?" And he said, yeah, that's the way it is. Like all of the stuff in quantum computing now, the The security services are all over it. And 100% fact that the security services are storing all of the world's RSA traffic. 100%. And it's like, if you're doing financial transactions, you care about that for 5 minutes, fine, use RSA. Use a 2048-bit RSA key. If you give a shit about that message being decrypted, as I say, 5 years from now, don't. Because every message you're sending now with an RSA key will be broken. 100% will be broken. Sorry, did I just scare the shit out of everybody? The question.
Could you please give an estimate how much computational like storage, in terms of storage, how much storage would that require to store all of the RSA encrypted traffic?
No idea. I don't think it's a factor though. I think storage is so cheap that it's happening.
Yeah, but then we produce so much data, and a lot of it is encrypted with RSA or let's say with TLS with HTTPS traffic.
Well, the answer is I don't know, but I'm 100% certain that somebody is storing it somewhere. I'm also 100% certain that even if nobody's deliberately storing your messages, it exists somewhere on the Amazon cloud or the Google cloud or somewhere. I don't know. It's there somewhere. It's decryptable in the future. I'm not saying that someone's deliberately looking at your emails. But I think it's happening. Anybody else? Thank you very much, everybody. It's been a pleasure.